Welcome to this deep dive, where we take a fascinating piece of research and really try to pull out the key insights for you. Today, we're looking at a paper that, honestly, it challenges something pretty fundamental in modern neural networks, especially transformers.
Yeah, it's tackling the whole idea of normalization layers, asking if we actually need them.
Exactly. The paper's called, very directly, Transformers Without Normalization.
And what really jumps out, I think, is the core claim that transformers, the backbone of so much AI right now, can actually work just as well, maybe even a bit better sometimes, without things like layer normalization or RMSNorm.
Which feels counterintuitive, right? We sort of baked those in.
Totally. And the way they propose doing it is, well, surprisingly simple.
It is. They introduced this technique called dynamic 10, DyT for short.
Right, DyT.
Think of it like a clever element-wise function, basically just a scaled version of the tan function we all know.
And they use it to just swap out the normalization layers?
Yep, direct replacement. And here's the kicker for everyone listening. These DyT-equipped transformers. They seem to get similar, sometimes even better, results across a whole range of tasks.
Without needing tons of extra hyperparameter fiddling, which is a big deal.
It really is. Could mean big things for efficiency. So yeah, we definitely wanted to unpack this one.
So our goal today really is to explore this idea for you. We'll walk through the paper, maybe give a little historical context on why normalization became such a big thing anyway.
Good idea.
Look at how this dynamic ton actually functions, and then, speculate a bit on what it all means for ML going forward.
Okay, sounds like a plan. So let's get into the paper's details. It kicks off by emphasizing just how common normalization layers are ever since BatchNorm landed in, 2015?
Yeah, 2015, it was huge. And the paper points out, specifically for transformers, layer normalization really became like a fundamental part of the recipe.
Absolutely. It's almost assumed.
And there's this widespread belief, which, anyone working in deep learning has probably absorbed, that these layers are just crucial for training.
Right, for optimization stability.
Exactly. Making things converge smoothly, especially when networks get really deep or really wide. It's almost like accepted dogma. You need normalization. The authors even mention how, researchers will propose really cool new attention ideas or whatever, but they almost always still stick those normalization layers in there.
But this paper forces you to pause and ask, why? Their key observation, and this is really interesting, is that if you actually look at LayerNorm inside a trained transformer,
what does it do?
It often behaves kind of like a Tom function. You see this S-shaped curve mapping inputs to outputs. It's not just linear scaling, it's squashing the extreme values.
Right, squashing those outliers.
Yeah.
And that observation seems to be the inspiration for DyT.
Exactly. So dynamic ton, the formula is DyTx equals correct tonx plus def.
Okay, let's break that down. So alpha is a learnable scalar, just one number the network tunes.
Yep. And gamma and beta are learnable too, but they're per channel, like in standard normalization.
Got it. So the core idea is that alpha learns how much to scale the input, and then tan just naturally squashes the big or small values.
Precisely. And it does this without calculating the mean and variance stats that LayerNorm or BatchNorm rely on.
That's the key difference. No statistics needed.
And it's designed as a simple swap-in. You just replace LayerNorm or RMSNorm with DyT.
And they claim, which is pretty appealing if you're building these models, that often you don't even need to mess with the other hyperparameters much.
Yeah, it really feels like a direct challenge to that normalization is essential idea.
Okay, so maybe it's worth taking a quick step back. Why do we get so attached to normalization in the first place? The paper gives a bit of background here.
It does. It mentions the general setup. Scaling with gamma, shifting with beta, using mean mo and variance sigma squared.
Right. And the differences between the main types. You have BatchNorm, common in CNNs, which looks across the batch and the features. Then things like group norm, instance norm, which calculates stats differently for different use cases.
But for transformers, the focus has really been on layer normalization, which calculates stats per token, per item in the square.
Right, token.
And also RMSNorm, which is like LayerNorm, but skips the mean centering. Simpler.
And RMSNorm has popped up a lot recently, especially in big language models. Llama uses it, as the paper notes.
Yep. And the paper's experiments mostly use LayerNorm, but they specifically switch to RMSNorm when testing on Llama to match its original setup.
Okay, so back to their core observation. This wasn't just a random guess about the tan shape. They actually studied trained models first.
Right. They looked inside things like Vision Transformer, VIT, Wave2Vec 2.0 for speech, and Diffusion Transformer, DIT.
And what did they see?
They found that in the earlier layers, LayerNorm looked pretty linear. Input goes up, output goes up, fairly straightforward.
Yeah.
But deeper in the network, those LayerNorm layers started showing that really distinct S-shaped tan-like behavior.
Interesting. So it changes depending on depth.
Seems so. And it might feel a bit weird because if you look at LayerNorm for just one token, it is doing a linear thing, subtract mean, divide by standard deviation.
Okay, yeah, that's linear per token.
Each token has its own mean and standard deviation, right? So the slope of that linear transformation is different for every single token.
Ah, I see. So when you look across all the tokens going through the layer.
Exactly. The combined effect starts to look nonlinear. It looks like that S-curve pulling the extreme values back towards the middle.
Gotcha. So the overall effect is nonlinear, even if the per token operation is linear.
Precisely. And their big hypothesis, the one that motivates DyT, is that this nonlinear squashing of extremes is the real reason normalization helps so much.
Not just stabilizing means and variances, but actively taming outliers.
Right. They argue that while most activation values might be in a nice central range, there are enough outliers, really high or low values, that normalization effectively reins them in.
And that makes sense for stability, especially in deep networks where values could potentially explode or vanish.
And they connect this to other recent work suggesting LayerNorm's nonlinearity actually boosts the model's representational power.
Oh, interesting. So it's not just about stable training. It might actually help the model learn better representations.
That's the idea. They even draw a parallel to biological neurons saturating, having a limited firing range, an old idea in neural nets, really.
Huh. A nice historical link.
Yeah.
So they visualize this too.
Yeah, they show Plodge looking at tokens and channels. For a single token across its channels, you see that linear transform, but the slope changes token to token because the variances differ.
Okay.
And when you look at a specific channel across all the tokens, you see that channels with really extreme value ranges are the ones getting squashed the most by the normalization.
Right. So it adaptively dampens the channels that are going wild.
Which leads them straight to proposing dynamic ton. Again, DyTx equals like ton x plus p.
With that learnable scalar alpha and the per channel gamma and beta.
The thinking being, alpha learns the right input scaling, ton does the squashing naturally, and gamma beta handle the final per channel adjustments, just like LayerNorm seem to be doing implicitly.
But crucially, it's not a normalization layer in the traditional sense. It operates element-wise. No statistics involved.
Exactly. It's mimicking the effect squashing outliers, keeping the central region mostly linear without the statistical machinery.
Okay, so how well does it actually work? They ran a bunch of experiments, right?
Oh yeah, pretty extensive. They took standard transformer architectures across different areas, swapped LN or RMSNorm for DyT, and mostly kept the original hyperparameters.
So like vision transformers on ImageNet.
Yep. VIT and also connex on ImageNet 1K for supervised learning. DyT performed slightly better or about the same as LayerNorm. Training curves looked really similar too.
Wow, okay. What about self-supervised, like MAE or Dino?
Similar story, DyT performed on par with LayerNorm there as well.
And diffusion models, like DyT for image generation.
Comparable or sometimes better FID scores with DyT. They did mention keeping the original affine parameters from LayerNorm in DyT, the ones used for class conditioning, but the core normalization was replaced.
Okay, still impressive. And the big one, large language models, Llama.
This is maybe the most striking result for many people. They tested Llama from 7B up to 70B parameters, replaced RMSNorm with DyT, performed on par, both in terms of the training loss curves during pre-training and how well the models did on zero-shot benchmarks afterwards.
That's huge. Did they have to tweak anything special for the LLMs?
A couple things. They added an extra learnable scalar right after the initial word embeddings.
Okay.
And they found that tuning the initial value of that alpha parameter in DyT was more important for LLMs compared to the vision models.
Interesting. But the core result holds comparable performance without RMSNorm.
Seems so. And they didn't stop there. Speech with Wave2Vec 2.0, DNA sequence modeling with hyena DNA and caduceus.
Different domains entirely.
And again, DyT held its own against the normalized versions. Pretty consistent picture across the board.
Okay, so the performance is there. What about other aspects like efficiency?
Good question. They looked at that specifically for Llama 7B, running inference and training on an H100 GPU.
Yeah.
The DyT layers were significantly faster than the RMSNorm layers they replaced. Reduced inference time, reduced training time.
That's a concrete, practical win. Faster training, faster deployment.
Definitely. They also did ablation studies, tinkering with DyT's design.
Like what happens if you take out the tan?
They tried that. Replaced tan with hard tan or sigmoid, performance dropped. Replaced it with just an identity function, so no squashing. A training diverged, it blew up.
So the squashing function is essential. Tan just seems to be a good choice.
Yeah, they suggest maybe its smoothness and being zero-centered helps. They also tried removing the learnable alpha. Performance dropped again. That learnable scaling factor seems crucial too.
Okay, so both the learned scaling alpha and the squashing tan are important parts of the recipe.
Seems like it. And they looked at what values alpha actually learns during training.
What did they find?
It closely tracks the inverse of the standard deviation of the activations coming into the DyT layer.
Whoa, okay, so 1 over the standard deviation. That sounds a lot like normalization.
Kind of. It suggests alpha is implicitly learning to scale things based on the activation spread, but maybe in a more global per channel way, not token by token like LayerNorm.
Huh. So it's like a learned approximate normalization baked into that scalar.
That seems to be the interpretation. They also compared DyT against other normalization-free methods.
Like fix up or skipping it, those initialization schemes.
Yeah, and weight normalization methods like sigma reparam. They tuned the learning rates for all methods fairly.
And DyT came out on top.
Consistently outperformed them on the models they tested, yeah.
Okay. What about initializing alpha? You mentioned it was important for LLMs.
Right. For most non-LLM models, the initial value, alpha 0, wasn't super critical. Something between 0.5 and 1.2 usually worked. Smaller values were maybe a bit more stable early on.
But for LLMs.
Much more sensitive. They found bigger models needed smaller initial alphas. And weirdly, using higher initial alphas in the attention blocks but lower ones in the feed-forward blocks actually helped performance.
That's specific. Why the sensitivity in LLMs?
They speculate it might be due to the massive width of these models, lots and lots of channels. Depth didn't seem to matter as much for the initial alpha choice.
Fascinating. And the paper also reviews related work, right? Contextualizing this.
It does. Covers theories on how normalization works, its role in transformers, and previous attempts to ditch it. They argue DyT is simpler to implement than many alternatives.
But it's not a silver bullet for everything. They mentioned limitations.
Good point. They found DyT struggled to directly replace batch normalization in older CNNs like ResNet 50 or VGG.
Why is that, potentially?
Their guess is maybe because those architectures use normalization way more frequently, like after almost every convolution layer, compared to how LN is used more sparingly in transformers, typically just before attention and FFN blocks.
Okay, so maybe the frequency or placement matters too.
Could be. So wrapping up the paper's main points, they really make a strong case that transformers don't strictly need normalization.
Yeah, DyT seems to work really well as a simple replacement. Matches or beats standard normalization across a lot of different scenarios.
It definitely challenges our assumptions and gives us new clues about why normalization seems so helpful in the first place. Maybe it was that squashing effect all along.
Stepping back, it really is remarkable how quickly normalization became dogma, wasn't it? BatchNorm in 2015 was such a game changer.
Oh, absolutely. Suddenly we could train much deeper networks reliably.
And then came all the variations, LayerNorm being key for transformers. It just became standard practice. You wouldn't even question putting it in.
The default assumption was, you need it for stable training, especially as models got huge.
Exactly. Most research was about tweaking normalization, not removing it. Getting rid of it entirely, especially in complex models like transformers, felt, well, pretty radical.
Which makes this paper so surprising. It really might shift how we think about building these models. It reminds you, doesn't it, of other times when things we thought were essential turned out not to be.
Totally. Like specific activation functions, maybe? And that connection they made between LayerNorm's S-shape and biological neuron saturation, that's a neat little echo of early AI history.
It is. So the core idea, this DyT function, is elegantly simple. It's not some complex new stats calculation.
Right. It's just an element-wise operation that seems to capture the effect we needed, taming those extreme values without the overhead of actual normalization.
And its success across vision, language generation, self-supervised learning, that suggests it's not just a fluke for one specific task.
No, it seems pretty broadly applicable. And those efficiency gains they reported, faster training, faster inference, that's a huge practical plus.
Especially with models getting bigger and more expensive to run all the time.
Definitely. And understanding how that alpha parameter learns to track the inverse standard deviation, That gives us real insight into how it's stabilizing things.
It makes you reevaluate what's truly necessary for depth network training. It's more than just removing a layer. It's about understanding the dynamics better.
Absolutely. And the real-world implications could be pretty significant for people working in this space. Faster, more efficient training for transformers.
Which powers so much stuff now, from LLMs to vision systems.
Think about the potential savings in compute cost, energy, development time, especially for those massive Llama scale models. Even small percentage gains add up fast.
And maybe simpler architectures, too. If you don't need normalization, that's one less component to worry about, to implement, to potentially introduce bugs.
Yeah, cleaner designs. Plus, it just spurs more research, right? Challenging assumptions like this always leads to digging deeper into why things work the way they do.
And maybe benefits for resource-constrained places, too. Deploying on edge devices where every bit of computation counts.
Could be. Every little bit helps there.
Okay, so now for our novel notions segment, where we brainstorm a bit based on the paper. This idea of potentially not needing normalization, it opens some interesting doors, doesn't it?
It really does. So, okay. Research idea 1. What if we stop thinking of DyT as just a replacement? What if we design new architectures from scratch without normalization, using DyT-like dynamic scaling as a core component?
You mean not just swapping it into existing blocks, but building new blocks around it?
Exactly. Could we design novel transformer blocks, maybe even CNN blocks, that intrinsically manage activation scales using these learned dynamic functions? Perhaps interleaving attention or convolution with DyT in new ways.
That's cool. It might lead to even better efficiency or maybe different learning properties altogether.
Yeah, and maybe it connects to that older work like Fix-Up or Skipping-It that tried to train deep nets without normalization using very careful initialization.
Right, those needed precise setups.
Maybe dynamic activations like DyT could handle those scaling issues more robustly, making training less finicky about the starting point.
Interesting. Okay, what's idea 2?
Research idea 2. Let's look closer at that learned alpha parameter in DyT. Could it tell us something deeper? Like, is it learning a measure of the dynamic range needed at different points in the network? Or maybe the information density?
Like a diagnostic tool almost.
Maybe. Imagine training one model on multiple different tasks. Would the learned alpha values show different patterns depending on the task demands in different layers?
Ah, so you could potentially see how the network is adapting internally for each task just by looking at the alphas.
Potentially. And maybe that could lead to new ways to adapt models for specific tasks or even guide automated architecture search. Like if a layer learns a very high alpha, maybe it needs more capacity.
Okay, that's heading into speculative territory, but it's a really neat idea using those learned scaling factors as signals.
Exactly. And of course, we should mention, these are just speculative research ideas, kind of for fun, sparked by the paper.
Right. Disclaimer noted. But it shows how thought-provoking this work is.
It really does. It reminds us that, deep learning is still evolving fast. What seems fundamental today might be questioned tomorrow.
And the link to the paper itself is in the show notes if you want to dive in deeper.
Definitely worth a read.
So the big takeaway here, I think, is pretty clear. Normalization layers, especially in transformers, might not be the absolute necessity we thought they were.
Yeah, DyT presents a really compelling, simple alternative.
With potential wins in efficiency, maybe simpler designs, and definitely giving us new insights into how these networks actually learn.
It really makes you wonder, what other assumptions are we making that might be worth challenging?
Exactly. What other essential components might turn out to be replaceable with something, well, simpler or maybe just different? Leaves you thinking, doesn't it?
It certainly does. A lot to chew on there.